All right, thank you. So again, I'm Evan Strasnick. I'm really excited to talk about Pinpoint, a PCB debugging pipeline using interruptible routing and instrumentation. Work done, of course, with my advisors, Sean Follmer and Maneesh Agrawala at Stanford. So printed circuit boards are at the heart of most of these devices that are comprising our computing world, like this projector PCB, which might be in the display I'm using right now, stretching my slides. And they have a number of advantages. They're compact, they're robust, they're easily mass-produced. But these PCBs also raise significant challenges in debugging. So to demonstrate the issues in debugging PCBs with current tools, I'll describe a small example board and some bugs that we might encounter. This is a simple game controller with a one-axis joystick on the left and a capacitive touch button on the right. So the first issue is access, or how easily we can observe or perturb behaviors within the circuit. Here I'm having a problem where moving the joystick has no effect on the signal, and so I'm attempting to probe the small pads beneath this mounted joystick with a common tool like a multimeter or an oscilloscope. The compactness of PCBs and surface mount components make simple observations like these both challenging and error-prone. Next, we identify issues of isolating parts of the circuit while debugging. Suppose I find a large amount of noise coming from somewhere in my circuit. The fastest way for me to identify the culprit is to just try disconnecting parts of the circuit and see how noise changes. But on a PCB, components and connections are fixed with solder, and so they can't easily be modified. So to isolate this capacitive sensing chip from its power connection, my best option might actually be to manually cut this trace. And finally, PCB debugging is hampered by a slow pace of iteration. It's likely the case that even if our capacitive button works on a prototype version of our controller, like a breadboard, the capacitive characteristics of the PCB will be different. So therefore, I'll need to adjust the value of the sensing capacitor shown here. And to do so, I have to desolder this component, as I'm doing here with tweezers and a hot air gun, and resolder a new one. Iteration is key to effective debugging, but unlike the more malleable breadboard, we can't easily try out solutions on a PCB without costly refabrication processes that can take days when working with a PCB manufacturer. So to address these three core issues, our key insight involves augmenting the PCB to make it more reconfigurable, and to shift the debugging process from using manual tools on hardware to using software. We do this by adding in jumper pads, pairs of test pads that we insert in series into connections in the circuit. We'll automatically instrument every connection in our game controller schematic with one of these pads. And in the result, each pin of each component will be separated from the rest of the board by a jumper pad. Our fabricated board will include these pads on the back side. And as we'll see, these jumper pads give us ways to address the core challenges. If we can probe them, we'll have easy access to all signals in our circuit. By controlling whether or not a pair of pads is electrically joined, we can isolate parts of the circuit at will. And if we can connect external circuit elements to any of these pads, we'll be able to insert and replace arbitrary components in our circuit, allowing us to iterate effectively. But before I explain how we enable these interactions, I'll quickly address existing solutions for improving PCB debugging. Our goals align with what we call in-circuit debugging, an ongoing challenge to utilize the more powerful tests at our disposal without reworking an assembled board. This includes various industry standard approaches like optical pipelines shown here for detecting structural issues, or built-in self-test capabilities like JTAG to run tests from the pins of onboard components. While these techniques provide ways of detecting particular bugs, fundamentally they can't modify the underlying circuit topology while testing, and therefore they don't facilitate isolation or iteration. Work from our community has addressed similar debugging challenges, but mainly within the prototyping stages of circuit design. The systems on the left all target breadboarded circuits and primarily improve access by visualizing voltage or current or code execution. But debugging does not stop with the breadboard. Making a PCB, in fact, brings all new bugs, such as when misrouting your pins or encountering defects in the board. Scanalog, earlier work from our lab, leveraged instrumented programmable boards to give designers a prototyping platform with full access, isolation, and iteration capabilities. But as programmable mixed-signal hardware is not yet common, we aim to bring these same types of interactions to conventional PCBs in a tool that can be used quickly and at low cost. Which brings me to the design of our current tool, Pinpoint. How does this actually work? Well, as before, our first goal is to instrument the user's circuit with those jumper pads. From a high level, Pinpoint's algorithm adds a jumper pad for each connection between a component and a net, or a group of electrically joined components. Here on the right, each component now can be individually isolated from the others. Pinpoint then determines where to place these jumper pads on the board, such that the backside of our game controller now looks like this. We'll find the best location for each pad using a simulated annealing algorithm with a cost function that minimizes factors like the lengths of additional routing required. But ultimately, we want programmatic control over the board's connections, and we want to debug in software with more powerful testing techniques. So for this, we need testing hardware that can operate on the jumper pads that we've put on the PCB. We call this hardware Pinpoint's control board. The control board connects the user's PCB with a software interface through which they debug. A set of analog multiplexers programmatically route jumper pads on the user's board to a USB oscilloscope and arbitrary waveform generator to not only probe the pads, but also inject test signals into them. Each jumper pad is bridged by a solid-state relay, which can programmatically open and close the corresponding connection. Control of these elements is all handled over serial communication with the software interface through an onboard microcontroller. But we need one last element to interface this control board to all of the jumper pads that we've put on the user's PCB and to complete Pinpoint. That final piece is a custom hardware interface for each PCB that we call the jig board. During instrumentation, Pinpoint also generates a design for a custom jig board that the user fabricates with their original PCB. The jig has pogo pins, which contact the jumper pads on the user's board. So, to debug, the user simply mates their game controller with the jig and connects it to the rest of Pinpoint's hardware. And so the entire system looks like this. The user's board, or what we call the device under test, is mounted on the jig board, which aids the control board in performing tests and observations. The user can then debug entirely within a software interface, which I'll describe in a moment. Now, revisiting our bugs from before, we can reflect on how this system addresses our core challenges. To observe signals from my thumbstick, I can simply click on them in a software interface. To isolate my capacitive sensor and determine its impact on noise, I can simply click on the corresponding jumper pad to open that connection. And to test out different capacitors on my board, I can open the surrounding jumper pads to disconnect the onboard capacitor from the circuit. And then, using a switchboard on the back side of the control board, I can insert arbitrary components, or even here an entire breadboard. On this breadboard, I can try out different capacitors until I find the ideal one for my circuit. So combining these core strengths of access, isolation, and iteration, Pinpoint then offers a number of more powerful testing features that I won't all be able to explain here. One important feature, however, is the ability to author and run high-level unit tests. A unit test combines actions like isolating a part of the circuit, injecting a test signal, and then measuring responses to make an assertion about the circuit's behavior. Unit tests are particularly useful in supporting iteration. When fabricating a new board, the user can run all of their previously authored tests to quickly verify its functionality. The user can author tests in a number of ways. Our initial prototype supports measurements of voltage, frequency, period, and continuity between points. Users can author these tests themselves using a scripting language, or they can import them from saved libraries. For tests that utilize test signals, users can define these signals using a standard set of waveforms, or by recording and replaying an observed signal, or by specifying a list of points. An example test might then look like this. The user specifies an assertion that there is no continuity between signal 1 and signal 2, and therefore this test will alert the user when an unintended short is found. Finally, when our controller is in working order, we can restore the PCB to a standard, always connected state by soldering across the jumper pads. We can always separate them again as needed if new bugs arise. So to summarize, Pinpoint is an end-to-end tool. It first intervenes during the design stage, performing an automatic instrumentation of the connections in the user's circuit. This stage automates a process that we call design for test, in which foresighted designers will often manually add dedicated test features to improve their access during later debugging stages. When the user fabricates their board, Pinpoint produces that secondary design for the custom jig board. The user fabricates these two boards together, or they can later produce the jig as needed with rapid prototyping methods. And finally, when testing, Pinpoint serves as test software, offering a graphical interface for probing and test authoring. That interface can carry out an entire debugging session without touching the hardware. This scope panel functions as a traditional oscilloscope view to visualize signals clicked either on the board or schematic representations of the user's circuit. Scattered across these views, we also see the interruptible jumper pads added by Pinpoint. By clicking on any of these points, the user can isolate parts of their circuit on demand. One simple but effective advantage of Pinpoint is that it links the board and schematic representations using metadata exported during the instrumentation process. So as a result, the user can do all of their debugging with references to their schematic design without needing to parse where those signals lie on their board layout. Below the scope lies a library of tests that the user has created or imported, and a command line through which they can author and run them. So we have additional details on the evaluation of Pinpoint in our paper, and we also walk through some representative examples of how we can instrument different types of circuits to debug different types of issues. For the sake of time, I'll describe just 3 of those here. These examples were all commercially available PCBs whose designs we downloaded and instrumented with Pinpoint. In this first example, we instrumented a very simple analog accelerometer PCB. The surface mount accelerometer is small, and so it's easy for a hidden solder bridge to form beneath the component like this. Using another built-in feature, Pinpoint can automatically detect common sources of error like these. The user's schematic specifies which components should be electrically connected and which should not. So with a single command that combines isolating parts of the circuit, injecting test signals, and measuring responses, the user can then generate a pairwise set of continuity tests for all the connections on the board, allowing us to automatically detect short circuits like these. In this next example, we're debugging a digital alarm clock to explore how Pinpoint can assist us in debugging physical input interactions. The issue we're having involves bouncing, which is our clock reports multiple inputs when we press this mechanical switch only once. And probing the event reveals several brief edges in the transition, as seen here. Since we've instrumented these push buttons, we can first verify that the rest of our hardware works in the absence of bouncing by disconnecting the actual inputs and injecting a clear digital signal with no bouncing to the microcontroller. Then we can capture the actual bouncing behavior from an observed input and then replay that test signal as needed while we tune our debouncing logic in software, saving us the hassle of manually repeating this input. In this next example, we instrumented an FM radio PCB to show how splicing and sub-circuit isolation can help us to divide up problems when debugging. So for example, when our audio is not playing, we might need to check each sub-circuit separately. First, we can debug the FM receiver by temporarily connecting its output to an external speaker that we know works. We can also debug the audio amplification stage by connecting an external audio source like an MP3 player to its inputs. So before I finish, I want to address some of the limitations of this prototype, as well as our next steps. Firstly, our paper discusses issues of scaling Pinpoint for large or complex circuits like this mobile phone PCB. Our first prototype supports a maximum of 16 jumper pads with 32 corresponding locations to probe. We can, of course, arbitrarily increase this limit by adding additional relays and using cascaded multiplexing. But for now, designers of large boards are able to specify which signals they want instrumented in this way. We also discuss free space requirements and how much space is needed when instrumenting a crowded board with this approach. Future versions of Pinpoint could provide intelligent assistance in cases where a designer must make tough choices about where to instrument. Also relevant in a discussion of scaling are steps of manual assembly for large designs. We've begun exploring new ways to fabricate and mate jigs without any manual assembly, such as using flexible PCBs like this, adhered to the board with Z-axis conductive transfer tape. Our paper also presents a detailed analysis of the parasitic factors introduced when instrumenting a PCB with Pinpoint. To summarize, our initial prototype works well with negligible impact on circuits like those that I've described in this talk, but we have not designed it for use with high-frequency circuits above the megahertz range. And Pinpoint's most fundamental limitation, perhaps, involves impact on the designer's original routing of traces during instrumentation. As I've said, Pinpoint introduces jumper pads such that any pin can be individually connected or disconnected from its net. In many cases, this objective requires adding new traces between components or moving existing traces, such as in this case where these 3 elements are connected on the same net. Therefore, when designers are particular about the routing on their board, they can manually correct routing following instrumentation on their own. So, with those improvements in mind, I'll finish by summarizing what we find most compelling about our current version of Pinpoint. It addresses the fundamental challenges of PCB debugging by improving access, isolation, and iteration in the debugging process. It enables high-level testing methods at low cost and with minimal overhead. After designing a PCB as usual, designers can simply run Pinpoint's instrumentation script and fabricate the jig to gain access to this full debugging suite. And it represents a step towards our larger vision of a world with fully reconfigurable hardware for rich interactive design and debugging. We hope that others will share in this vision so that we can effectively support designers and students and fellow researchers as we continue to produce the next generation of devices. So with that, I want to thank you all again for coming, and I would be happy to answer questions.
Yep, questions. Just raise your hand and we'll hand you a microphone. Yep.
Hi, Dan Ashbrook, University of Copenhagen. This is really cool. One of the big issues here, I think, is the construction of the custom jig for every single board. I'm wondering if you thought about a way to standardize a jig. If you ran if you didn't care about messing with the routing and put all of the pads in one particular location in a pattern.
Yes. So let me sort of explain more about the jig and a few ways that we go about with that assembly process. So firstly, the way that someone actually constructs the jig is you can hand assemble with these pogo pins, and of course these are all routed to the header row that we attach to the ribbon cable. If this is sort of a laborious assembly process, we have a rapid prototyping method that I didn't talk about, where essentially you can laser cut your own jig using any material, insert those pogo pins into the slots, and then simply connect it with jumper wires. That's a quicker solution, and it's obviously low cost, but that leaves a jig that's sort of less persistent for future debugging sessions. I think you're absolutely right that manual assembly is one of the sort of points of friction that we really want to address to make this really easy to use. As I've said, our sort of holy grail is to make jigs that you don't have to do any assembly at all. You simply print it onto a flex PCB and sort of adhere it to the board. I agree that having a standardized pattern would be it would simplify this process a lot. You could have one jig, but as you know, we've done a lot of interviewing and working with designers and professional designers and researchers, and everyone's very particular. There's sort of an art to the creation of your board and its routing. So the sort of least that we can disrupt your particular routing, that's our goal, and that's why we put some effort into this algorithm of sort of optimizing where those paths go. But that's a great question.
Hi, I'm Dave from Dr. Mouse. I like this work pretty much, but I wonder because you propose previous was Scanlog and some work propose breadboards, and now this work propose using PCB. So how do you think in the futures how makers will do their prototypings?
Yeah, that's a great question. I myself am very passionate about taking this sort of richness of interaction and extending it across really the whole design process, which I think extends starting from the beginning, where you sort of envision your circuit, you specify its behavior, create a design, maybe a simulation, and then you prototype on a breadboard, and then eventually you end up here with sort of a fine PCB. And so I think that something that's really important is that we sort of connect, we have an infrastructure that allows us to tie together all of those pieces of the process. I think right now we end up, we create these sort of one-off solutions for maybe prototyping on a breadboard or a simulation tool, and a lot of the information that the user puts in, or the specifications that they make, or even the problems that they solve, that information all gets thrown away, I think, when we sort of move from one to the other. So my goal, as you're saying, is to take these same types of interactions with Scanalog, with Pinpoint, to start them as early as we can, so that when someone first starts their circuit, they have all the support, and then every time they create a test or they gather some data, we can carry that information all the way through. When you've built your prototype, we already can help, as we've seen with autocomplete, we can help suggest things to do in the circuit. So I think there's a lot of work to be done, really from our whole community, in taking these types of solutions that work for one